you definitely want to make sure that you know for the final exam. You should know what a Taylor series is, and so if you have some function, f of x, that function can be written as a power series that looks like c0 plus c1x plus c2 x squared plus c3 x to the third plus dot dot dot, where Cn is equal to the nth derivative evaluated at 0 divided by n factorial. And this was our power series that was centered at 0. And then the other option is that we have f of x is equal to c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a to the third plus dot dot dot, where Cn is equal to the nth derivative evaluated at whatever that x value a is. And so this is our power series that is centered at x is equal to a. So the top one, whenever we take our power series and make our coefficients, and find our coefficients by using this formula, then that power series is called a Maclaurin series. And if we center at just a generic x equals a, then this is called a Taylor series. And so the Maclaurin series is a special case of the Taylor series, but it's important enough that we actually give a special name, and we honor the guy that came up with the power series centered at 0. So one comment is you might be saying, well, why do I care about, if I have some series that centers at 0, why don't I just always center at 0 and then not worry about this centering at some other x value? And the answer to that is that, remember when we talked about those power series that had those ends that flopped up and down, maybe another end that kind of went up to an asymptote or something like this? So the picture's going something like this. And so things are going on there. Now, that series converged on a particular interval. And even if it took negative infinity to positive infinity and your series converged to the function over the entire interval, well, if we center at x equals a and we're interested in approximating a function near x equals a, then we can use less terms if we actually center at x equals a, if we're interested in the function values around x equal to a rather than x equal to 0. So that's why we may have this second value, this second series down here. All right, so we have the Taylor series and the Maclaurin series, and we can write down maybe the first 5 or 6 terms for the Taylor series, or the first 5 or 6 terms for the Maclaurin series. And so after doing the practice problems, you should be able to do that for, given the first 5. So if I said, okay, find the Taylor series for natural log of x, centered at x equals 0, and then I asked you to write down the first 5 terms, then hopefully you could do that. Now we also have some special Maclaurin series to memorize. And so I'd like you to know the Maclaurin series for 1 over 1 minus x, e to the x, sine x, and cosine x. And those are 4 Maclaurin series that you definitely want to have memorized. Okay, so first question is, are there any questions on any of the practice problems, either from the regular power series section or the Taylor and Maclaurin series sections?
I have one question on number 11. The Cn terms end after the third.
This is in what section is this?
8.7.
Okay.
And so you don't really have a series, right? You just have those 3 terms.
Right. So number 11 here in 8. I'm not going to do the problem, but I do want to write it down here. So 8.7 number 11, we have a function that is f of x is equal to 1 plus x plus x squared, and we are centering at an a value of 2. And so what you're going to find out is that after about maybe the second or the third term, the rest of your coefficients are all going to be 0. And so you'll still have a series, it's just that your series happens to have an infinite number of zeros at the end of it rather than interesting terms.
So the book didn't put it in a series form, they just left it with those 3 terms?
And that's okay.
Okay.
Once if all the rest of the terms are all equal to all coefficients of 0, you just don't have to write them down. Yeah, that's totally fine. And that makes sense too because we're approximating a polynomial with a polynomial, so you don't need higher degree x terms to approximate a quadratic polynomial. Okay, other questions or comments? Okay. So I left you with one piece of math candy to suck on over the weekend that had to do with Maclaurin series and Taylor series. And the bonus was to find the Maclaurin series. Find the Maclaurin series for arctangent of x. And the hint was that the integral of 1 over 1 plus x squared dx is equal to arctangent of x plus c. All right, anybody have any thoughts on this? Did anybody think about this over the weekend at all?
Wasn't it that we just take the integral of the terms of that series that was 1 over 1 plus x squared? So we would take the integral of, we'll look at every one of those values in that particular series. And all of those.
Yeah, so this seems like a really reasonable idea. So I don't know anything about the arctangent function, and I could use that formula, the Maclaurin series formula that says that Cn is equal to the nth derivative evaluated at 0 divided by n factorial. But because I know that the antiderivative of 1 over 1 plus x squared is arctangent, then what I might do is use my knowledge about 1 over 1 plus x squared, and I can use my knowledge about this function by taking the 1 over 1 minus x and morphing it a little bit. And so this guy over here, the very first thing I might do is say, okay, 1 over 1 plus x squared looks kind of like 1 over 1 minus x. And I know that 1 over 1 minus x has the Maclaurin series 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th plus ... And so if I want to come up with a power series for 1 over 1 plus x squared, well, I can rewrite 1 over 1 plus x squared as 1 minus a negative x squared. And then everywhere that I see an x in this original expression that I have up here, I can replace that with the stuff inside the parentheses with the negative x squared down below. And so I've got 1 plus negative x squared plus negative x squared squared plus negative x squared to the 3rd plus negative x squared to the 4th plus ... All right, so are there any questions on what I've written down here? Okay, so once I've written this down, I'm not done writing out the Maclaurin series. I need to clean this up so that I have a number plus a coefficient times x raised to a power plus a coefficient times x raised to a power. So when I clean this up, what's going to happen is that I'm going to end up with an alternating series because I'm going to have a plus and a minus and a plus and a minus depending on whether my power is even or odd. And I'll end up with 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, and then my pattern's going to continue from there. All right, are there any questions about writing that part down? So here's the cool bonus part, and that is that we now have that 1 over 1 plus x squared is equal to all of this stuff. Turns out that we can integrate on both sides of this thing. And so we can write down the integral of 1 over 1 plus x squared dx is equal to the integral of 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus dot 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 dx. And there's a theorem that says that you can integrate term by term on these Maclaurin series, and the antiderivative, integrating term by term, is going to be the same as the antiderivative of the function that we're using as our Taylor series. So our antiderivative over here is arctangent of x plus c. And on the right-hand side, when I take my antiderivative, I end up with x minus x to the 3rd over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 8th over 8 minus dot dot dot. This should be a 9, because when you add 1 to 8, you get 9. Thanks. Yeah, these should all be odd. Okay, cool. All right, now, I opted to put the plus c over here on the left side. It doesn't matter. I do not want to put a plus c on both sides because I'd have a c1 and a c2, and then I just combine them together anyway. So I might as well not use plus c on both sides. I'm just going to put it on the left side, and I chose the left side because it's shorter. It doesn't go on forever. It would be hard to write my plus c at the end over here because there is no end to it. Okay, so we're nearly done. The last question is, what should this c be for our particular example here? Does anybody know what the arctangent of 0 is equal to?
Just 0.
Yeah, the arctangent of 0 is equal to 0. And so by knowing this, since we know that the arctangent of 0 is equal to 0, if I plug in 0 for x, then on the right-hand side, I end up with a whole bunch of zeros. So we've got arctangent of 0 plus c is equal to 0 minus 0 cubed over 3 plus 0 to the 5th over 5 minus 0 to the 7th over 7 dot dot dot. So if I fill in a 0 for x, then I've got arctangent of 0 is 0. And so I have 0 plus c is equal to a whole bunch of zeros added together. And so if I solve this equation for c, what do I get? This is a very hard equation to solve. 0 plus c equals 0. C equals 0. These were sure. Okay, so we get c equals 0. All right, so what that tells us is that we really don't have to worry about this c here. And so in the end, the arctangent of x is equal to x minus x to the 3rd over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9 over 9 minus dot dot dot. And so this is one cool way. We can use integration. We can also use derivatives to use our knowledge about Maclaurin series to come up with Maclaurin series for new series, or for new functions. All right. Any questions or comments about that? Alrighty. Then that wraps up Chapter 8. Two brief topics that I'd like to discuss before we wrap up all the new material, and those two topics are in Chapter 9. And both of these topics are important for Calculus 3. So this is kind of like a 2-minute, well, maybe 2-hour introduction to some stuff that you're going to see in Calc 3. And so today we're going to talk about sections 9.1 and 9.2, which are about parametric surfaces. Parametric curves. I have Calc 3 in the brain. Parametric curves and calculus. Alright, so last class I threw up at the end of, I didn't throw up, I put up on the board here, that would have been gross. I put up on the board here an example of a digitized Etch-a-Sketch. And the idea was that we controlled the horizontal and vertical motion of your Etch-a-Sketch drawing by turning these dials. And that's kind of the idea behind parametric curves. And so here's our definition. A parametric curve is a curve C that can be described by parametric equations. So this is a really unsatisfying definition, right? What is a parametric curve? Well, it's a curve that can be described by parametric equations. Well, what the heck are parametric equations? Okay, so parametric equations are equations that come in pairs. They have an x and a y. And x is going to be some function of t, of some variable t, and y is going to be another function of t. So x equals g of t and y equals h of t, where g and h are functions of t, and that t value, that's our parameter. Okay, so our first example is the one that I showed as a picture on Mathematica yesterday, or on Wednesday. And we had x is equal to t squared, and y is equal to t cubed. And oftentimes, when you're given this pair of equations, these are parametric equations. I know they're parametric equations because I have an x and a y, and both the x and the y are functions of some variable t. Oftentimes, we're given boundaries for that parameter. So I might be told that t is between -2 and 2. And so then I might want to try and draw a picture of this curve. And the way that I want to do this is that I want to create a table for myself where I have t as my input, and then I have an ordered pair as my output. And so, for example, if I allow t to be equal to -2, then my ordered pair looks like -2 squared, comma, -2 to the third. And so that output is that I end up with 4, comma, -8. So I get an ordered pair, the x value is 4 and the y value is -8. Are there any questions on where I came up with that ordered pair from? Okay, so I can now plot that ordered pair. 1, 2, 3, 4, 5, 6, 7, 8. So I need to move 8 units down on the y-axis and 4 units to the right on the x-axis. And so I have this point down here. All right, I might also plot a couple of other points. So let's make a table here of maybe just the integer values. So we'll look at -2, -1, 0, 1, and 2. And so we'll plug in -1 for the x, so we'll have -1 squared. And then we'll have -1 to the third. And so we end up with 1, comma, -1. And so I can plot that point as well. questions about this table right here? Please go ahead and fill in the last 3 XY ordered pairs, and then check with your neighbor and make sure that you agree with your neighbor on his or her ordered pairs as well.
Yeah, this is that shape, the shape from Show's.
Once you get those ordered pairs, check with your neighbor and see if you agree with your neighbor. For your third order, or the one with t equals 0. 0, 0? All right, how about for t equals 1? 1, 1, and 4, 8. Okay, so we've got 3 ordered pairs, 0, 0, 1, 1, and 4, 8. Do I have a second on these ordered pairs? Great. Okay, so I can go ahead and plot those points over here, and notice what I'm doing is that I'm marking each point with my parameter t, and so when t equals 0, I'm at the origin, which is 0, 0. When t is equal to 1, I am located, my point is at 1, 1, and when t is equal to 2, when t equals 2, my point is located at 4, 8. So what I kind of imagine in my head is that what these are telling me is that they're giving me a curve on an Etch-a-Sketch, and they're saying, okay, I'm going to turn my dial in a fashion where my horizontal dial is described by t squared and my vertical dial is described by t cubed. And I can think of the location, these points, as the location of some sort of particle traveling along the curve. Now, it's not at all clear that this is how the curve goes, but it turns out that this particular curve is shaped like this. So if I really wanted to know what that curve looked like, then I could plot some more points there and connect the dots in a much better way. Okay? But a couple of things that you might notice about this curve. Number one, this curve does not pass the vertical line test, so this is not a function of x. This is a function of t, though, because the x and the y are both determined by t, but this does not pass the vertical line test. Okay, so let's take a look at this on your calculator. So please pull out your calculator. Okay, so I briefly mentioned this on Wednesday, but I want to talk about it in a little more detail here. If I want to plot a parametric curve, what I need to do is I need to go to, first of all, mode. And on the fourth line down, you'll see function, parametric, polar, or sequence. And so the second one over is PAR for parametric, and you want to select that. And then once you've selected parametric, then you can quit out of the mode. And then when you hit y equals, up here in the upper left-hand corner, instead of getting y1 equals, y2 equals, etc., you get an x value and a y value, and it tells you that the input variable is going to be t. So in this case, I'm going to type in t squared, and notice that my variable button down here, when I hit that, it automatically types in a t rather than an x because we have this in parametric mode. Okay, so we have t squared, and then the y value will be t cubed. And the first thing I'm going to do is I'm going to go ahead and hit zoom, and I'm going to go down to zoom standard. And take a look at the picture that we ended up with. with our choice of zoom standard, we ended up with that top half, but not the bottom half of this particular curve. So once you've done that picture, go to Window, and there's a couple of things that are going on here. The x minimum and maximum and y minimum and y maximum are negative 10 to 10 and negative 10 to 10 like they are in your regular graph for the calculator. The t minimum and the t maximum are what we want to focus on. The standard or the default has t going from 0 to 2 pi, and the reason for that we'll see in our next example. But we can change those t minimums and t maximums so that t goes from negative 2 to positive 2. The next mark down below that is t-step. And what the t-step does is that tells the calculator how many points to plot. So if you want to have a connect the dots that's really nice and smooth, then you want this t-step to be pretty small, like 0.13, which is what they give us. If you want to have a picture that looks like a kindergartner's connect the dots, where the dots are really far apart, and like when you make a snowman, it turns out to be like a square, and then another square because the dots are so far apart, then change your t-step to something like 1. And you can make it an even better and smoother curve if you make the t-step even smaller, but the price you pay is that it takes a really long time to graph. So, all right, so we graph, and we get this curve. And notice that the curve actually stopped. Okay, because we only went from t-values from negative 2 to positive 2. And so if I hit trace on this, I get 3 values that show up. I have my t-value, which in this case is negative 2, and it tells me the x and the y coordinate for when t is equal to negative 2. I could type in negative 1 for t, hit enter, and now my cursor is up here at 1, negative 1. And it tells me my t, my x, and my y. Okay, any questions or comments about that? So one last thing that you can do with this particular graph is that if we go back to the y equals, and you move your cursor over to the left of the x and y's, right now it's on a sort of a diagonal slash. And if I hit enter, the first time I hit enter, it makes that slash bold. And if I hit enter a second time, it gives me something that looks kind of like a little key. What that is a little circle at the end of a line segment. So watch carefully what happens now that I have that little key picture up there when I hit graph. I'll hit it again. So what's kind of cool about that is that that little circle highlights how the curve is being traced. And so you can think of that little circle as the particle that is moving along this path given by x equals t squared, y equals t cubed. All right, any questions about that?
Why does changing the window from negative 2 to make the bottom part show up?
So if I had, well, let's see here. So if I do this trace here, why does it make this part down here show up?
Yep.
So the reason is when we drew this picture here, the original window, the default on the calculator went between 0 and 6 point something or other. And so that started at t equals 0 and only plotted t equals 0, t equals 1, t equals 2, etc. So to get this bottom half, this curve comes from the negative t values. And so when I plotted only from 0 to 6, I didn't have those negative t values in there.
So the standard zoom on this window is negative 10, the positive 10, the normal is 0 to...
Well, it depends on what it is. So the standard zoom for the x values is negative 10 to 10, that's the viewing window, and the y values go from negative 10 up to positive 10. But the t, the time values that you're plotting, the t values, the standard is from 0 to 2 pi. T is not standardized as negative 10 to 10. All right, other questions?
What do you do with that circle, then it's no longer going
It probably what's happening, what's that? Yeah, so probably what's happening is it becomes a little less smooth, and so if you want to fix that, you can go to your T-step and make that T-step a little bit smaller. So for example, if I do 0.05 and I hit graph, it moves a little bit slower, but it still goes into that origin, and here it's coming out. And there it is. So that's really an issue of the calculator is not quite as accurate as it might be. So yeah, so you do pay a price for that little circle and make sure your picture a little less accurate. Other questions? Okay, so let's take a 10-minute break. When you come back, we're talking about 9.1, which is parametric curves, and then after about the next 10 minutes, then we'll get into the calculus of parametric curves. Okay, so here is a algebra pop quiz. X squared plus y squared equals 1. What is that the equation of?
Circle.
The equation of a circle, absolutely. And so this is, in particular, a circle whose radius is 1. Now, there just so happens to be a fabulously cool trig identity that is very closely related to the unit circle, and that just so happens to be cosine squared theta plus sine squared theta equals 1. Okay. And so this is the coolest trig identity ever. Okay. And so if you kind of look at these, there's a lot of similarities between the two of these two equations that are written up here. And so if by looking at these two and kind of staring at them for a little while, I can come up with parametric equations that seem pretty natural to say, let's let x be equal to cosine of, well, theta is my variable up here, but I'm going to go ahead and use t. We're going to let x be equal to cosine of t, and I'm going to let y be equal to sine of t. And so, by looking at these two equations right next to each other, this seems like a pretty reasonable idea. And so, if I go ahead on my calculator, and I look at y equals, and then I say x, let's let x be equal to cosine of t, and let's let y be equal to sine of t. Now, first thing I'm going to do is to draw this in my standard window, so I'm going to do a zoom standard. And this gives me a little itty bitty circle because the x is going from negative 10 to 10 and the y is going from negative 10 to 10. And we only have a circle with radius 1 drawn on this thing, so it's a pretty tiny circle drawn up on the board up here. Now, in this particular case, notice that we got the entire circle, and our t-values go from 0 to 6.2, which is approximately 2 pi. That makes complete sense because we're using our parameter to measure the angle that around our circle. And so as t increases from 0 to 2 pi, we're swinging all the way around our circle. And so parametric equations, x equals cosine of t, y equals sine of t, for t between 0 and 2 pi, will give us a circle with radius equal to 1. And what's kind of cool about this is that if I want to throw a number in front of this, for example, if I want a circle with radius 5, all I need to do is put a 5 in front of my cosine and a 5 in front of my sine. And so we've got 5 cosine of t and 5 times the sine of t. And now when I graph, I end up with a circle with radius of 5. Now, up on the board up here, it looks, or up on the screen, it looks a little bit like an egg. It's not a perfect circle. If I really wanted to have a perfect circle, I would have to go down to zoom square. And that's going to give me something that looks a little bit more like a circle rather than an egg. And so, in general, what I can write here is that a circle centered at 0, 0 with radius r has parametric equations x equals r cosine t, y equals r sine t. And if you want to get the entire circle, then your t value should go between 0 and 2 pi. Notice if my t value goes from 0 to 4 pi, so if I change my window, my t minimum goes from 0, my t maximum is going to be 4 pi. And I graph, and you need to watch the graph because this is kind of important in terms of what happens up here. So my t minimum is 0, my t maximum is 4 pi. Here we go. All right, so we are now at t equals 2 pi, and we just go around the circle twice, so we just overlap our path. And if I wanted to look at that and hit trace, then I can actually follow my t values down here, starting at t equals 0. And if I press the right-hand button, my t values are increasing. Oh, here we are at t equals pi over 2, which looks like about 1.57. Notice that my finger is on the right-hand button on the arrows. Even though my particle is moving along this path to the left, what I'm doing is I am increasing my t value, so I'm pressing to the right on my arrow. So here we are almost at 2 pi. Yep, there it is, 2 pi. And then I can continue on. Okay, so I can kind of follow along my path and see my t values as I move along, as the particle moves along the path. Okay, any questions about that? Okay, so then the final example of some parametric equations. Both of the examples we've looked at so far do not pass the vertical line test, and so they're both cool examples that you could not have written as f of x equals stuff in terms of x. But it turns out you can take any of the old stuff that you knew, y equals cosine of x, y equals x squared minus the absolute value of x, any of those functions, you can take those and you can write them as parametric equations. So, for example, if I have y equals x squared, we can write this as parametric equations. And the way that this works is that when I look at the original function, y equals x squared, I know what that looks like. That's a parabola. And on the original function, x is my independent variable, and y is my dependent variable. And so what I do is I allow x to be my parameter. So let x be the parameter t, because in y equals x squared, x is the independent variable. So we'll let x be equal to t, and then y, well, y is equal to x squared, but since x equals t, then y equals t squared. Okay, so these are my parametric equations, which are going to describe, we hope, this parabola right here. Now let's say that I want to graph this parabola from an x value of -10 to an x value of +10. Since x equals t, that means that in order to draw this picture, I need for t to go from -10 to +10. And so we'll do x equals t, y equals t squared. And then on my window, I want my t minimum to be -10, my t maximum to be 10. And just kind of thinking about this picture that I have here, my x values, I went from -10 to 10, so I can view my entire x-axis. And my y values, how high should I make that y? Yeah, it makes sense to make that y value up to 100 because, for example, when x equals 10, y equals 10 squared, which is 100. So we'll put our x minimum as -10, our x maximum is 10, our y minimum as 0, and our y maximum at 100. And hopefully life will be good. And yep, we get our problem. All right, any questions about that? Going once? Going twice? Okay. All right, so now we've looked at a couple of examples of some parametric curves that come from parametric equations. And so the next thing we want to look at is calculus on parametric curves. And the big question that we want to answer is a question that works if we are looking at these curves as paths that a particle is taking. So, for example, here we might be interested in how far has the particle traveled from time t equals -2 to time t equals 2. To answer that question, the question of distance, what we need to answer is, what is the length of this curve that we've created? So the two questions that we're asking are, how far has a particle traveled? Are there 2 L's or 1 L in traveled?
Two.
All right, how far has the particle traveled along its path? And another way to ask that question is, how long is the parametric curve? That's some good music. Okay, so to answer this question, what we want to do is we want to look at sort of a generic parametric curve. And the way that this works is maybe I've got a curve that looks something like this. Okay, there's my curve. Notice that I made my curve so that it does not pass the vertical line test because parametric curves do not need to pass the vertical line test. And we'll say that at our starting time, we'll call our starting time t equals a, and we'll call our ending time t equals b. And so the particle is moving from the point located at time t equals a and ends at the point located at time t equals b. And in order to figure out how far that particle has traveled as it moves along this curve, we want to find the length of this curve. And the way we're going to do that is we're going to take this curve and we're going to break it up into line segments. Okay, so the idea. The idea is to break the curve into line segments that approximate the curve. Now, each of these line segments, well, it's really hard for me to figure out arc length along a curve, but I can always figure out the length along the line segment because it's the distance between my 2 points. And so the idea is that I'm going to break the curve into line segments that approximate the curve and find the length of each line segment. once I've found the length of each of these straight line segments, then I'm going to add them all up. Add up the lengths of the line segments. And that sum is going to approximate the length of our curve. So how are we actually going to make that happen? Well, the idea is the following. I'm going to take one of these segments, I'm going to take this one right here, and I'm going to zoom in on that one little segment. And so that one segment looks something like this. And so if I look at this picture here, then I can actually create a right triangle with this line segment that I have, and I can call this vertical distance delta y and this horizontal distance delta x. And this distance along the hypotenuse we're going to call delta s. And s is, the reason we use s is because s is our variable that we use for position, and so delta s is a change in position. Okay, so on this picture that I have drawing right here, delta s is approximately the length of the curved segment. And because I have this right triangle here, I've got that delta x squared plus delta y squared is equal to delta s squared. Okay? Got myself the Pythagorean theorem going on. Alright, so that's kind of cool. I can describe the length of this curve that's inside of this little bubble here. That delta s I can describe with delta x squared plus delta y squared equals delta s squared. So that equals that little arc length inside of my circle squared. Now, if I do this, but instead of having really long segments, if I break this up into segments that are very, very, very tiny and very, very little, infinitesimally small, then instead of having delta x and delta y and s, if I let the number of segments go to infinity, those segments get very, very tiny, and what I end up with is a picture that looks something like very closely approximated like this, and instead of having delta y, I have dy, and instead of delta x, I have dx, and instead of delta s, I have ds. And so as I allow that number of segments to go off to infinity, each segment gets very, 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 very tiny. And so we can approximate this length of our segment of the curve with ds, where ds is equal to the square root of dx squared plus dy squared. Alright, so what we've just done here is that we've broken the curve into line segments that approximate the curve. We found the length of each line segment, and then we want to add up the lengths of those line segments. And so our arc length, the length of our curve, is going to be adding up all these little ds's. So I've got ds, and I'm going to add up all of those little ds's across my curve C. So I have the integral over C of ds. And the way I'm interpreting this is ds is my little bit of my curve length. My integral sign is that I'm adding up all those little curve lengths, and I'm going to add them up across our curve C. Okay, so that's pretty useful as a formula in the sense that it's pretty and you can identify all the pieces that are a part of it, but that's not very useful in terms of calculations, and so calculation-wise, I can replace ds with square root of dx squared plus dy squared. But even this integral right there looks totally weird. I mean, in terms of this class, I have never seen a dx or a dy that are thrown inside of a square root. I mean, they're always at the end, right? Like, I mean, we always have the integral stuff in the middle and then a dx at the end. And those were, and the integral and the dx were our bookends of our integral. And here they're right in the middle. And so this particular version is also a little bit unsettling. And so what we need to do is we need to do one more transformation of this guy. And so what you might notice is that if I have ds squared is equal to dx squared plus dy squared, then I can do something here that's kind of cool. On the right-hand side of this equation, I'm going to multiply the entire right-hand side of the equation by 1. Now the form of my 1 is what's interesting. I'm going to multiply the right-hand side of my equation by dt squared over dt squared. Totally legit because I'm just multiplying by 1, so I haven't actually changed anything. And so I've got ds squared. And here's the next funky thing that I'm going to do after I've multiplied by 1. I'm going to distribute the bottom of that 1 inside of the parentheses, but I'm going to leave the top outside of the parentheses. And so if I do that, I end up with dx squared over dt squared plus dy squared over dt squared. And then I still have a dt squared on the outside. Alright, so inside of the square brackets I can write this as dx over dt, quantity squared, plus dy over dt, quantity squared, and then I have dt quantity squared on the outside. And all of that is equal to ds squared. Alright, now it's not at all clear why this is useful, but are there any questions about how I came up with this formula? Okay? So why is this useful? Well, over here I've got ds squared is equal to all of that. If I take the square root of both sides, I get that ds, which is our little bit of arc length along our curve, is equal to the square root of dx over dt squared plus dy over dt squared times dt squared, and all of that is under my square root. And in terms of algebra, because this first part is multiplied times the dt squared, I can take the square root of each part separately, and so the square root of dt squared is just dt, and so I end up with ds is equal to the square root of dx over dt squared plus dy over dt squared times a dt at the end. And so this makes life super cool, because I can take my arc length formula up here, which is the integral of all of the s's of my curve C, and I can write that as arc length is equal to the integral of ds, well ds is equal to all of this stuff, integral of the square root of dx over dt squared plus dy over dt squared, and then a dt at the end. And now my variable at the end is a t, which means that my bounds can be from my starting t value to my ending t value. And so my bounds will go from A to B. All right, so we took this idea over here, adding up all the little arc lengths, and we translated it into something that looks an awful lot worse. I mean, it's definitely not as pretty as the original one, but this one over here is much more useful in terms of our calculations. So let's look at an example. Alright, so in this example, we want to find the length of the curve y equals x squared on the interval where x goes from negative 10 to 10. Okay, so the very first thing I notice is that I'm given a regular old equation y equals x squared, and I know that that's a picture of a parabola. Here it is, and I'm interested in this parabola from x equals negative 10 to x equals positive 10. And I want to find the length of the curve in between those 2 points. Okay, so in order to do this, step number 1 is to write down parametric equations for our curve. Alright, so I look at this curve, and we looked at this as an example earlier, and so I already know that my parametric equations are x is equal to t and y is equal to t squared. If I didn't know that, then I could look here and say, oh, this is a curve that's described by y being a function of x. So x is my independent variable, so I'll let x be my parameter. And y will be equal to, well, whatever y is equal to, but replace the x's with t's. And since x had to go from negative 10 to 10, our t value is going to go from negative 10 to 10. Okay, so we've come up with parametric equations for our curve, and we have bounds for the t values. Step 2 is to set up the integral. And so our length will be equal to the integral of the square root of dx over dt squared plus dy over dt squared with a dt at the end. Alright, so some information that we need to fill in on here. Let's start with the dx over dt and the dy over dt. Well, I need to go back to my parametric equation. So I need to write down my parametric equations first, which we've already done. And I know that x is equal to t. And I know that y is equal to t squared. And I need to figure out the derivative of x with respect to t. So I take the derivative of t, and what do I get when I take the derivative of t? Yeah, I get 1. And my derivative of y is dy over dt, and that's equal to 2t. Okay, so I now have these two values, and I can go ahead and plug them into my integral. And so my length is going to be the integral of the square root of 1 squared plus 2t squared and a dt at the end. setting this up here, I just need my boundaries, and my t boundaries are going to be from -10 to +10. And so now I have a very nice integral, which is just going to describe the length of this curve right here. Any questions or comments about that? All right, so now I want to solve this integral. And in terms of our examples that we're doing with parametric curves, maybe I would want to start by simplifying a little bit. I have the integral from -10 to +10, square root of 1 plus 4t squared, and a dt at the end. And this does not look like a nice integral that I'm really excited to find the antiderivative of. So this would be a good place to approximate this integral using your calculator. So does everybody know how to use your calculator to evaluate one of these integrals? So the first thing you want to do, there's a couple of different ways to do this. One is to graph the function in the middle. The other Okay, so if I want to figure out what the integral is as an approximation, I can go to math, and then if I scroll down far enough, I get to number 9, which is fn int. And I can now plug in my function. So I've got my function that I'm going to integrate. So let's see here, I'll do square root of 1 plus 4t squared. And then I'm going to put a comma. And then I'm going to integrate with respect to t. And I'm going to integrate from -10 to +10. Now, what you might notice is that my variable up there is t, and that's because my mode happens to be in terms of parametric equations. If your mode was on regular functions, then when you press that variable button, then you get x rather than t, and it doesn't really matter which letter you use. And then I hit enter, and it crunches for a little while, and then it gives me a number. And so my arc length, my length of my curve, is approximately equal to 202 units. Right. Any questions or comments about that?
How does this relate to, I guess, a circle? Comes into the circle? Because I'm seeing like the parallelism a little bit between that and the formula for the circle.
So if we were to let's say that we had a circle, and just to use the example of the circle we had before, let's say that we had a circle with radius 5. And we'd like to find the circumference of this circle. So find the circumference of the circle with radius 5. Well, the easy way would be to use geometry, and so our circumference is equal to 2 pi r, which in this case is 5, and so we have 2 pi times 5, which is 10 pi, so that's our geometry version. And ideally, if we set up an integral, we should end up with the same answer. So our integral, well, the very first thing that we might do is that we would parameterize our curve, and so we want a circle with radius 5, so x would be 5 cosine t, y would be 5 times the sine of t. And in order to get the entire circle, our t values will go between 0 and 2 pi. Okay, so there's our parameterization of our curve. So our arc length, our length, is going to be the integral from a to b of the square root of dx over dt squared plus dy over dt squared, and then a dt at the end. So now we need to fill in a bunch of information. Let's start with the dx dt and the dy dt. So x is equal to 5 cosine t, y equals 5 sine t. So our derivative, dx over dt, is going to be negative 5 times the sine of t. And our dy dt, the derivative of y with respect to t, is going to be 5 times the cosine of t. Okay, so now we can go back to our length up here. And so our length will be the integral of the square root of dx dt squared, so negative 5 sine of t, quantity squared, plus positive 5 cosine of t squared, dt at the end. And our t values, to go all the way around the circle, t will go from 0 to 2 pi. All right. So we've set up our integral to describe the circumference of the circle. Now, if life is good, if we can integrate this thing, we should end up with, integrate and then plug in the boundaries, we should end up with 10 pi. So let's see if that happens. You can double check on your calculator. But I think we can do some pretty cool trig on this one as well. So check this out. The integral from 0 to 2 pi, if I expand my integrand a little bit here under the square root, then I have 25 sine squared t plus 25 cosine squared t, and I have a dt at the end. Does anybody see anything that we could do here to simplify this, Ben?
Well, if you pull the 25 out, then sine squared t plus cosine squared t is just 1.
Yeah, so we've got the integral from 0 to 2 pi of the square root of, we can factor the 25 out, and we get sine squared t plus cosine squared t, which is the most fabulous trig identity ever, because sine squared t plus cosine squared t equals 1. And so we are left with the square root of 25, which, by the way, is 5. And so we have the integral from 0 to 2 pi of 5 dt. Now that is really easy to integrate. Antiderivative of 5 is 5t. We're going to evaluate between 0 and 2 pi. And so we plug in 2 pi for our t, and then we plug in 0 for t, and we end up with 10 pi. So it's a little bit more work than just using our 2 pi r, but we end up with the same value, so that's a good thing. So now you can go and impress your friends with your new way to find the circumference of a circle. All right, any questions about that? Okay, so I want to wrap up class here with your very, very final turn-in homework assignment.